Okay. So, welcome back to the lecture series of finite volume, and what we are in the middle of the discussion of the discretization of convection diffusion system. And so far what we have discussed is that the central difference scheme and the upwind scheme and the downwind scheme, and the important message that has come out of that, it is a trade off between your stability and the accuracy. What we have looked at is that central difference scheme is highly accurate, I mean it is second order accurate, but it is not that way stable, or rather it does not provide you the accurate solution. I mean, and the other way, once you look at the upwind scheme, that is stable, but the accuracy is an issue. So, now today that actually provides the platform for discussion of the higher order scheme. So, we will now look at the higher order scheme in the system. So, what higher order upwind scheme? So, this essentially uses the information of your upwind scheme. So, it is some sort of an upwind biased interpolation scheme. So, now and what is the genesis of that? Because of the genesis is that the accuracy and stability of the other scheme like CD, upwind and all these schemes. Now, what this scheme is aiming at, it producing at least a second order accurate solution. So, it would be accuracy wise, it would be second order and also it stable. So, it uses both the advantages of upwind and CD scheme, and then we formulate this kind of scheme. Now, while doing that, this also uses, if you look at that one dimensional stencil, this is your C, then that would be your cell interfaces. So, these are the cell interfaces. It uses the similar kind of stencil. This is, I mean E, West, WW, this is EE. So, it uses similar kind of stencil in a one dimensional system, but now once the important property which associated with the flux at the interface is that the element C and what it follows. Now, to get an upwind kind of system, one can say that the ahead of this one, instead of E, you can say it is a downstream of that if the flow field is in this direction, and the flux at this particular element faces, this is the F, then the Vf is in this direction. So, it is a, then this should be the upwind information of that, and instead of this you can say this is upwind, and instead of this you can say it is a downstream. Why? The reason is that you are interested in this particular cell, and at this particular phase where the flow field or the flow velocity direction is in this direction. So, the weight of the upstream cell would be important or predominant compared to the downstream cell. So, that is the convection, because this is the upstream cell, this is the downstream cell, and the values which will correspond to this value is phi C, this value would be phi U, this value would be phi UU. So, that follows our standard notation system phi DD. So, this is what one can use. So, similarly, one can see if the velocity is in this direction rather. So, this is our C, and if you have an element like that, and for example, let us say for this element faces, at this phase the flow field goes in this direction, the Vf is in this direction, then this is the cell face and it goes in the this direction, this is D, this is upstream of that, this would be the upstream, this will be the downstream. So, in this case the cell velocity was in this direction. So, these are counted as upstream nodes. So, these are all upstream elements and these are downstream element, while the cell speed is this way, then these are considered as an upstream and these are considered as downstream. So, depending on the direction of the flow field, one has to decide which will be the upstream elements and which will be the downstream elements, and accordingly you can define your the variables in that fashion. So, now we will start with a second order upwind. What we have seen the standard, that is a first order upwind. Now, we will start with second order upwind. So, one can say it would be second order upwind SOU scheme. So, how you go about it? You can define in one dimensional stencil like that, let us say like this, and in between that you have C. So, you define your cell interfaces like that. So, this will be the cell elements associated with that. Now, at this particular element, this is the phase and the value which is upstream of it, let us say this is U, this is UU, this is D and this is DD. So, if you consider the value between all these, so they will go like that. So, this will have phi D, this is phi DD and this is where phi U, and they would be some sort of an phi C, phi F and this is phi UU. So, all these informations are now stored, and why we are saying this is upstream, because at the phase we are assuming the flow field is in this direction. So, the mass flux is positive at that particular phase. So, you start with a linear profile. If you start with a linear profile, then the system you can define as phi x equals to k naught plus k 1 x minus x c, because whole idea is to find out the phase value at these f phases, and fitting it to the nodal values x c, x u and all these, one can write that phi x equals to phi c plus phi c minus phi u divided by x c minus x u into x minus x c. So, that is how you define this system. Now, what happens then at phi f, which is essentially phi at x f, equals to going to be phi c plus phi c minus phi u divided by x c minus x u multiplied by x f minus x c. So, that is how you get the phase value, and if you have a uniform grid, then this guy will boils down to, for uniform grid, this phi f will boils down to 3 by 2 phi c minus half phi u. So, that is the special case if you have uniform grid to calculate this information. Now, one has to look at the discretized system and how. So, if you look at the discretized equation, then one needs to calculate the like m dot E phi E, which is going to be 3 by 2 phi c and minus half phi w. So, this we are looking at the system where one has assuming the equation which is convection diffusion equation, which is a convection diffusion equation on uniform 1D grid. So, that is why you write these things and multiplied with m dot E 0 minus 3 by 2 phi E minus half phi E E multiplied with minus m dot E 0, and then you get the similarly m dot W phi W equals to 3 by 2 phi C minus phi E by 2 multiplied with m dot W 0 minus 3 by 2 phi W minus phi W W now multiplied with m dot W 0. Now, this if you substitute in the discretized equation that we have obtained earlier, now discretized system or equation, if you add put those things back there, this will get you back phi W minus m dot E minus 3 by 2 phi E minus phi E E, then minus m dot E plus 3 by 2 phi C minus phi E by 2 m dot W minus 3 by 2 phi W minus phi W W by 2 minus m dot W 0 minus gamma S by del x E phi E minus phi C minus gamma S by del x W phi C minus phi W equals to 0. So, which will lead to the discretized form like A C phi C plus A E phi E plus A W phi W plus A E E phi E E plus A W W phi W W equals to 0, because there is no source term. So, the discretized equation will look like that. Since it is a, so when we looked at that, it was a first order system, we had only this much. Now, because of the second order, you get 2 more points ahead and downstream. In this, AE is flux Fe, which is minus gamma E is by del x E minus 3 by 2 m dot E 0 minus m dot W 0. A E is flux F E, which is half of minus m dot E 0. Now, A W equals to flux F W, which is gamma W S W by del x W minus 3 by 2 m dot W 0 minus half of m dot E 0, and similarly you get A W W equals to flux of F W W half of minus m dot W 0, and A C, which is the summation of all the fluxes, which is flux C F, that will get you gamma A C by del x C plus gamma W is W by del x W plus 3 by 2 m dot E 0 plus 3 by 2 m dot W 0, which one can write with negative sign AE plus AW plus AEE plus AWW plus m dot E plus m dot W. So, this for a continuity equation to be conserved, this will go away. Now, the truncation error. So, the truncation error one can estimate equals to. So, for this kind of scheme, as we have used for the upwind scheme or central scheme, one can follow the similar procedure, and what one can obtain, this will be 3 by 8 delta x square phi c triple prime minus 1 by 4 delta x cube phi c fourth derivative and so on, which indicates that the higher order term is of delta x square, which is essentially second order accurate in spatial discretization. Similarly, if you look at the stability of this particular scheme, what you can obtain, that right hand side of the convection term equals to minus 3 by 2 phi c minus half of phi w multiplied with m dot E 0 plus 3 by 2 phi E minus phi E multiplied with minus m dot E 0 minus 3 by 2 phi c minus phi E by 2 multiplied with m dot w plus 3 by 2 phi w minus phi w multiplied with m w 0. So, the rate of change of right hand side with respect to phi c would get you minus 3 by 2 m dot E 0 minus 3 by 2 m dot w 0. So, which is always negative and indicating that this scheme is also stable. So, with the second order upwind scheme, you can somehow come out of those problems with both the central difference and the upwind scheme, and this particular scheme, essentially the SOU scheme, is not only stable, it also gives you second order accuracy. Now, in the similar direction, one can devise another scheme which will call the quick. Quick is quadratic upstream interpolation for convection kinematics. So, that is what the quick stands for. So, again if you look at a stencil like that, where this is the cell, then you have, it is the downstream of that, it is upstream of that, and then this is further upstream, this is DD, and at the cell face you can say the Vf in this direction and this is the phase value. So, using this and this value, one can calculate the profile. So, this is phi c, phi f, phi d, phi u. So, all the information of the neighboring elements are taken into consideration. So, what as the name suggests, the polynomial would be quadratic polynomial. So, that is where the interpolation is going to be obtained, and what profile one can obtain from this, you can assume the phi would be or phi x would be some sort of a k naught plus k 1 x plus k 2 x square. Now, which will say that at you have these phi values at different at phi e at x equals to x u, it will be phi c at x equal to x c, it is phi d at x equals to x d. So, now you need 3 points to find out the coefficients, the 1, 2, 3, k 0, k 1, k 2. So, in order to find out those coefficients, you need 3 set of information, and if you put this back and solve it, what one get, phi equals to phi u plus x minus x u, x minus x c, x d minus x u multiplied with x d minus x c, phi d minus phi u plus x minus x u, x minus x d, x c minus x u, x c minus x d, phi c minus phi u. Now, if you have uniform grid, then this boils down to at phi f it becomes phi c plus phi d by 2 minus phi d 2 phi c plus phi u divided by 8. So, for uniform grid the phase value becomes like that. Now, using this for the same uniform case and 1D the convection diffusion system, if you put it, you calculate that m dot e phi e, which is going to be 3 by 4 phi c minus 1 by 8 phi w plus 3 by 8 phi e, which is now m dot e 0 minus 3 by 4 phi c phi e 1 by 8 phi double e plus 3 by 8 phi c multiplied with minus m dot e 0. Similarly, you get m dot w, which is 3 by 4 phi c minus 1 by 8 phi e plus 3 by 8 phi w multiplied with m dot w 0 minus 3 by 4 phi w 1 by 8 phi w w plus 3 by 8 phi c multiplied with m dot w 0. So, this is what you get. Now, again after getting this information, you put everything back in the discretized equation. Now, once you do that, the discretized terms would look like 3 by 4 phi c minus phi w by 8 plus 3 by 8 phi e, that is the first term, multiplied with m dot e 0 minus 3 by 4 phi e minus phi e by 8 plus 3 by 8 phi c multiplied with minus m dot E 0 plus 3 by 4 phi c minus 1 by 8 phi E plus 3 by 8 phi w multiplied with m dot w 0 minus phi w by 8 plus 3 by 8 phi c. So, is all the term what we have calculated now putting back in the discretized system, and then left with the diffusion term which is gamma s by del x E phi E minus phi c gamma s by del x w phi c minus phi w which is 0. So, then the discretized form will become again looks similar, but the final discretized form will have the different coefficients. So, it will be A E phi E plus A W phi W plus A E E phi E E plus A W W phi W W. And the term A E equals to flux F E, which will be gamma E A C by del x E minus 3 by 4 m dot E 0 plus 3 by 8 m dot E 0 minus 1 by 8 m dot W 0. A W would be similarly, it is flux F W, which is gamma W S W by del x W 3 by 4 minus m W by 0 plus 3 by 8 m W 0 minus 1 by 8 m dot E 0. So, the pattern for these coefficients are pretty much similar if you can notice, but the thing is that these are looking similar as we have assumed or what we are deriving here for the uniform grid system. If the grid is not uniform, when it is non-uniform, these terms would look completely messy or rather complicated, but the formulation will not change. Only thing you will get to see the differences in the coefficient calculation. Now, A W W equals to flux F W W equals to 1 by 8 minus m W 0. So, A C is F N B C flux C F equals to gamma E A C by del x E plus gamma W S W by del S W plus 3 by 4 m dot E 0 minus 3 by 8 m dot minus E 0 plus 3 by 4 m dot W 0 minus 3 by 8 m dot W 0, which is again minus A E plus A W, A W W, A E E plus m dot E plus m dot W. So, we will stop here today and we will take from here in the follow up lectures. Thank you.